Hello everyone, welcome to today's video lesson. We're going to be going over exponential graphs, and this can be found in page 101 of the textbook. The methodology we're going to be using to unpack this type of graph is the same as that used when we went through parabolas and hyperbolas. We'll start off with the simplest case, and then we're going to change some variables and add new variables and see how this impacts the overall shape of the graph. So as just a little description on exponential, exponential means growth on previous growth. So for example, we can think of a newborn baby, and it grows very rapidly, grows on its previous growth. Also, it learns exponentially, learns based off things it learned the previous day, learns very fast, grows very fast. Exponential growth can also be used to describe something like a virus spreading through a population. So we'll begin with our simplest case, y equals 2 to the power of x. So actually this case can be used to describe a virus spreading through a population. If we let x be the number of days, day 0, day 1, day 2, day 3, and y be the number of infections. So on day 0, we have the first person infected, patient 0. The next day, day 1, this infected person infects one other person. So now there are 2 infected people. On the second day, each of these 2 infected people infects one other person. So now we have 2 plus 2 infected people, 4 infected people. On the third day, each of these 4 infected people infects one other person. So we have 4 plus 4, 8 infected people. So we can see a pattern here in the y values. The number of infections doubles each day. And that's why it can be represented by this base 2 to the power of x. So let's check some of the values. If x equals to 0, we substitute this into our equation, y equals 2 to the power of 0, which is 1. If x equals to 1, y equals 2 to the power of 1, which is 2. If x equals 2, y equals 2 to the power of 2, which is 4. And lastly, if x equals 3, y equals 2 to the power of 3, which is 8. So you can see these values correspond. And now we're going to include some negative values for x. So this is our theoretical understanding of the graph y equals 2 to the power of x. In our practical case, x needed to be positive because days needed to be positive. In our theoretical example, we can make x negative. So let's check if x equals minus 1, y equals 2 to the power of minus 1. Now, our rules for negative exponents tell us we must flip it and change the sign. So y equals 1 over 2 to the minus 2 to the power of 1, which is half. So you can double check this on your calculator. If x equals minus 2, y equals 2 to the power of minus 2. So our rule says we flip it and change the sign from negative to positive. So 2 to the power of 2 is 4, so this comes out to 1 over 4. You can also check it on your calculator if you're not familiar with this. So we have our list of x values and our list of corresponding y values. So if you plot these on a graph, I've made my x-axis minus 2, minus 1, 1, 2, 3, and my y-axis is going up in 2s. So this is just to save a little bit of space so this graph can fit. Now, if you are sketching a graph like this, you can do it roughly, like how I've done it on the board, even freehand if you're comfortable. The reason being is that you're just trying to determine the shape of the overall graph. If you try to work things out exactly, it might take a little bit too long. And if ever I ask you in a test or exam to draw a graph, I will give you graph paper where everything is measured out perfectly, and then you don't have to measure, you just have to plot on the graph paper. So let's just describe this graph a little bit. You can see the rapid growth over time, so that is a feature of exponential growth. Another thing we can see is that this graph is getting smaller and smaller, but it looks like it's never quite reaching zero. So let's understand that concept a little bit. So for x values, as the x values are getting more and more negative, this graph is still positive but getting smaller and smaller. So let's check. If we have an x value of minus 10, y is going to be 2 to the minus 10, which is 1 over 2 to the 10. So this is a very small fraction. We have 1 in the numerator, 2 to the power of 10 in the denominator. It's a very small number, not quite 0, just above it. Let's take a value of x which is even more negative. If x equals minus 100, y equals 2 to the negative 100, so y equals 1 over 2 to the power of 100. So this fraction is even smaller than the previous one, because our denominator is 2 to the power of 100, and our denominator there is only 2 to the power of 10. So this is a much, much smaller fraction. So you can see our y values are getting smaller and smaller, but it will never quite reach 0. So remember, positive fractions, it can never be 0. So in other words, this line over here, the x-axis, is called the asymptote. It's whenever a graph tends towards a certain value but never quite reaches it. And you would have seen examples of asymptote when we covered hyperbolus. So this video is just going to be a little introduction on exponential graphs. In the next video, I'll change a few parameters, and in the last video, I'll do a couple of examples.